MAVEN is a spacecraft that's orbiting Mars. It's been there since 2014. MAVEN, in this case, is an acronym. It stands for Mars, Atmosphere, and Volatile Evolution. And this gives a clue as to what MAVEN's real goal is. It's to study the top of the atmosphere and how the gases in the top of the atmosphere might escape from Mars away to space.
So the atmosphere of Mars must have been a lot thicker about 4 billion years ago, and today it's very cold and dry. And MAVEN is meant to understand the atmosphere as it is today and how it has evolved into this current cold, dry state.
One of the things we're trying to understand with MAVEN is whether a magnetic field for a planet is important for regulating the climate or allowing the planet to keep an atmosphere. Earth has a global dynamo magnetic field. Mars does not, but Mars has an induced magnetosphere. It has an induced magnetic field.
The upper atmosphere of Mars is being ionized by solar radiation. And so the electrons are being stripped from the atoms in the atmosphere. When that happens, it turns into what we call a state of plasma. This plasma in the upper atmosphere is very conductive. It leads electric currents to flow through it. Electric currents, they shape the magnetic fields that are around them. And that's actually how we see them with MAVEN. We take magnetic field data and we map it around the planet, and from that, the currents emerge. We've known how the currents flow in the Earth's magnetosphere for decades, but we don't know how that works around Mars. We don't know how it influences the interaction with the solar wind, because it determines how energy is flowing into the atmosphere, how it's transferred from the solar wind into the system. And that's what we're trying to do with MAVEN. When you just look at the data as it comes down, you're just seeing a little squiggly line, essentially. You're seeing the magnetic field strength and its direction vary as the spacecraft is flying through different regions. And so what you have to do is you have to actually map it to the planet and to this interaction with the solar wind. And then it starts to emerge that you have a drape situation where the magnetic field of the solar wind encounters the planet and it starts to wrap around it. And the reason it wraps around the planet is those electric currents that we are seeing.
The magnetic field in the solar wind is straight lines. You can think of straight spaghetti noodles, and it's flowing towards the planet, and those spaghetti noodles wrap around this basketball-shaped planet. And that's indeed what we saw in the data, the magnetic field lines draping around Mars as a planet. One thing that wasn't so expected was the specific configuration of the electric currents that we derive from the magnetic field data. If Mars is a ball here, it's sort of this cup shape on the day side that loops back on itself, maybe something that looks like this. What wasn't so intuitive to me was the directions of those currents and the fact that it wraps continuously around to the night side, and it makes this marvelously complex current system on the night side as well.
This is the first time that we've been able to actually map out the currents. So we can see where the energy is being transferred, we can see what actually forms the underlying mechanisms creating these induced magnetospheres that are not just common here in the solar system, they're 50% of the planets that have them, of the terrestrial planets. And if you want to understand how the atmosphere of Mars and Venus, why they're so different from the Earth, and why they're so different from each other despite both being non-magnetized, we need to understand their induced magnetospheres first.
So knowing how these global current systems are configured teaches us about how charged particles near the planet are going to move, both charged particles in the solar wind and charged particles from the atmosphere itself that are in the process of escaping to space. So now we can understand better where those particles came from, how they move near Mars, and where they're going to go next. That in turn teaches us about atmospheric escape from the planet and the history of the atmosphere over time. How thick has it been? How much has been removed?